So for this one, I'm taking so long. Wow. It's really taking forever. It's still spinning. I got the spinny wheel. Do I have too many things open? Is it angry about that? There we go. Okay. So acids and bases, there are different models out there. The one that AP focuses on is the Bronsted-Lowry. Arrhenius was like the first model that they came out with. In his model, he said that acids produce hydrogen ions and bases produce hydroxide ions. But the problem is that it doesn't allow for many of the reactions to be classified as acid and base. And also, the other place that this kind of fell apart was one of your typical bases is NH3, which is ammonia, but that's a base. But yet you can't produce OH ions from this guy because he doesn't have any oxygen. And so his model kind of fell apart. There's another model out there called the Lewis model, and he's the same guy that came up with the Lewis dot diagrams way back in chapter 8. If you go on to college, a lot of times in college, they'll make you use that one. But for AP and for what we do in here, Bronsted-Lowry is what we focus on. So Bronsted-Lowry said that acids are hydrogen donors and bases are hydrogen acceptors. So during your acid-base reaction, a proton is going to be transferred from one molecule to another, and these end up being reversible reactions. So if you look at this reaction, remember the last time I showed you when I was talking about this with the ammonia, I said that that's where Arrhenius kind of fell short. Here, this works. So what I tell people to do with Bronsted-Lowry is find the ones that look like twins, okay, or look like siblings. So this guy and this guy look similar, right? See the similarities between them? And then which one has more acid in, or which one has more hydrogen in it? This guy does, right? So this is your acid, and we call this stuff on this side conjugates. So conjugate acid. And then you can see that these guys belong together, because if you think of this as HOH, which one of these has more acid? Well, this guy does. So this is your acid. And this is your base. This is going to be your conjugate base then. That makes sense? Find the pairs. Which one has more hydrogen out of that pair? That's your acid. And what happened is that he donated, because remember, it's acids or donors. he donated a hydrogen to this guy. And because he got rid of a hydrogen, he looks like this. And these are actually reversible reactions, so they go both directions. That makes sense? All right. So each reactant and the product it becomes is called a conjugate pair. So when an acid gives up a proton, what remains is the conjugate base. When the conjugate base accepts a proton, what forms is a conjugate acid. So I think that there's room there for you guys to write those down. That makes sense? No? All right. Good? Okay. All right. So here you can see here that this would be our acid. This is going to be our conjugate base. You can see that each one has lost a hydrogen in transitioning. And then the reverse is over here. This becomes a base, adds a hydrogen in. Oh, honey. Okay. So that a base accepts a proton and becomes a conjugate acid, and an acid donates a proton and becomes a conjugate base. Make sense? Good? Okay. Oops. So here, I think you've got these on your sheet there at the bottom. So see if you can figure out and just write A, B, CA, or CB. So acid, base, conjugate base. How'd you do on those?
Number 4.
Number 4. So you can see where these are related, right? Look at the anions here. See how they're related? This one has more hydrogen, so that's going to be your acid. This would be your conjugate base.
Yeah, I have.
And then here, these are related. This one has more hydrogen than this guy, so this has to be the acid, and this the base.
Oh, okay.
Make sense?
Yeah.
Mm-hmm. All right. Certain things, certain substances, not all, but certain substances can be amphiprotic. Okay. We also call that amphoteric. Sometimes it's referred to as amphoteric. Amphi means both. So like if you have an amphibian, it has life in the water and out of the water. Okay. Amphibious. Different types of vehicles can be amphibious. So they have, like in the military, they have these things that are or like in the Dells where they have the ducks. The vehicles that they call the ducks up there.
Oh, yeah.
They are out on the road, and then all of a sudden they go in the water, and then they're a boat. Okay. So those are amphibious. So amphi means both. And certain substances can be amphoteric or amphiprotic, meaning that they can act like an acid in certain situations and a base in others. And water is an example of that. Sometimes water will end up being a base, and sometimes it'll end up being an acid. So down in this case, we've got it as a base because over here it's going to form H3O plus. And down here, it's going to act like an acid because it's going to end up giving away a hydrogen to this NH4. Okay, makes sense? So water can go either way. Other substances like sodium hydroxide or hydrochloric acid, those things can only go one way. All right. I think I'm still doing this one today. So, yep, amphiprotic or amphoteric. It's sometimes referred to when it's used as a solvent in a solution. And this is what the ionization of one water molecule would look like. One note that I want to point out is sometimes you will see this written as H3O plus, and other times you'll just see it as H plus. But it's the same thing. It's used synonymously. I think that's where you're at, is on the second page there.
The first thing on your page says, what two equations show how water auto-ionizes? Equation 1, equation 2.
So these are your equations. This is equation 1. This is equation 2. Okay, good. All right. We have a KW, which is the ion product for the dissociation of water for pure water at 25 degrees Celsius. This does change based on temperature. It doesn't include water, and a very small value means not many ions are present. Only about 2 out of 1 billion water molecules actually goes through this ionization. And what that was, this is the equation from the previous page where we had the H plus OH minus. So I'll let you write down what you need to write down, and then we'll talk about that.
So, you want to know the equilibrium constant? Is that the equation?
Yes, it's this right here. Because it started out with KW equals.
Okay, that's what I thought. I just want to make sure.
And I'll talk about what that means after you write it down, because if I try to talk while you guys are writing, it's hard for you to listen. Good? No? Let me know when you're done.
I'm okay. I think I'm not really sure what this right now, so I know.
Okay, so these square brackets here mean concentration. And when we do these KW and KA values, okay, we always take the products over the reactants, but we don't include water. So that's why there's only these two things here. So the molarity of your H plus concentration and the molarity of your OH multiplied together is going to give you this value for water at 25 degrees Celsius.
Oh, so that's the value of the.
Yep. This is the value. And that equals the concentration of each of these. Okay. So if we wanted to know the concentration of each of these, if we made each one of those X, for example, okay, if I had this as X and this is X, then X squared would equal this guy. And then I could find out the value of X by doing what? How would I solve for X? If this is X squared, how could I figure out X? Not divide. Huh? Not divide, no. If this is squared, what's the opposite of squaring something? Square root, right. So if I want to know what X is, I'm going to take the square root of this value. And the square root of that value is going to be 1 times 10 to the negative 7. So in a neutral solution, H plus equals OH, that's going to equal 1 times 10 to the negative 7.
What are the values? Do you want that? Like,
So yeah, the third one from the bottom, it would equal this amount. So it's a neutral solution. Okay, and then in an acidic solution, you're going to have your H is going to be greater than this value, and your OH is going to be less than that value, and then it flips when you're doing a basic solution. And we'll get into more of that tomorrow with tomorrow's notes. And then your homework tonight is 18.1 in your packet.